Welcome to this explainer, where we are going to treat your Cambridge physics exam exactly like an archaeological dig. We're going to uncover the hidden clues in the questions, layer by layer, to reveal the absolute perfect answers. So I want you to imagine this for a second. The clock is ticking in the exam hall, you can hear the invigilator pacing, the tension is building, and you finally open up your past paper, whether that's syllabus code 0625, 0651, 0652, 5054, or 9702. Now, I want to introduce you to two types of students I see literally all the time. First, we have Alex. Now, Alex is brilliant. Alex studies for hours and overloads every single answer with raw physics facts. We're talking dumping an entire encyclopedia onto the page, but providing absolutely zero analysis. It's just a wall of text. Then, on the other hand, there's Sam. Sam gets nervous and rushes through the paper, completely missing the specific requirements of the command words, dropping easy marks everywhere just across the finish line. Honestly, we have all been an Alex or a Sam at some point, right? Seeing those red pen marks all over our return papers and just wondering where on earth we went wrong? Well, today we are going to transform those red marks into green check marks.
Okay, so let's really dive into this. Having raw physics knowledge is absolutely great. I mean, you definitely need to know your formulas and your definitions, but listen to me carefully. If you don't know exactly what the examiner is asking, you are going to lose marks, period. You might write a beautifully correct, scientifically accurate paragraph about the density of water, but if the question just asked you to state an equation, well, you've just wasted precious time and energy that you needed for the back page of the exam. The real challenge we face today is bridging that massive gap between what you have stored in your brain and what you actually write down on the paper. We need to stop throwing random facts at the exam, hoping something sticks, and start targeting our knowledge like an absolute laser beam.
Here is exactly how we are going to do it. 1. Cracking the physics code. 2. Forces, springs, and state. 3. Calculating the limit. 4. Pressure under the surface. 5. Explaining the why. And 6. Your physics success blueprint.
Let's start with Section 1, cracking the examiner's secret language. This is the absolute core of your exam strategy. If you don't understand the language, you literally cannot play the game. The crucial point here is that these command words are your roadmap. They dictate whether you need to give a quick fact, a step-by-step mathematical proof, or a highly detailed logical argument. Top students don't just read the topic of the question, they hunt for the command word first. And to completely master this, we use the PEAL framework. That stands for Point, Evidence, Explanation, Link. Depending on the command word, you might only need to drop the point, or for higher mark questions, you might need the entire PEAL structure. Now, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's see how this framework actually looks in action.
Moving on to Section 2, let's look at our first major physics concept from the syllabus and see exactly how they test it.
As you can see, forces have the incredible power to change the size and shape of an object. Just think of a kicked football compressing momentarily as the boot strikes it. That is a compressive force causing an elastic deformation because, it pops right back to its original shape. Or think of a bungee cord stretching all the way out. That's a tensile force in action. If that cord became permanently stretched, it would lose all its springiness, and the jumper would stop incredibly abruptly instead of bouncing, which obviously would be terrible. That permanent change is called inelastic deformation, and it happens to things like the metal panels of colliding cars. The physics here is pretty clear, right? But how do we actually answer exam questions about it?
Well, this is exactly where our friends Alex and Sam usually crash and burn. Let's compare state versus calculate. If the command word is state, you just express the fact in incredibly simple, clear terms. For example, if the paper says state the equation linking pressure, force, and area, the perfect full-mark answer is literally just P equals F over A. That's it. 1 point, boom, move on. But Alex would write a whole paragraph about atmospheric pressure, wasting 3 minutes. On the flip side, calculate means you have to work it out from the given figures, showing all your steps. You absolutely must provide the formula, substitute the values in, and give the final answer with the correct units. If Sam just scribbles down a final number in a blind rush without showing the steps, the examiner literally cannot award partial marks if that final calculation is even slightly off.
All right, Section 3. Let's step up the difficulty and see how we handle those trickier calculate questions.
When you were asked to calculate something like spring extension, you'll very often get a data table just like this one taken straight from a Hooke's Law experiment. What the examiner is really testing here is if you actually understand the physical difference between the total length of the spring and its actual extension. So we're going to do a quick data scan challenge right now. I want you to imagine you have 60 seconds on the clock to extract the core trend from this table.
Time's up. To find the extension, you can't just look at the final length. You have to follow these exact steps. Step 1. Note the original unloaded length. Looking at our data, at 0.0 newtons, that was 24.0 centimeters. Step 2. Measure the new length of the stretched spring. At a load of 1.0 newtons, the length is 24.6 centimeters. Step 3. Subtract the original length from the stretched length. So, 24.6 minus 24.0 gives us an extension of 0.6 centimeters. And look what happens if you double the load to 2.0 newtons. The extension perfectly doubles to 1.2 centimeters. This exact proportional increase is what the examiner wants you to spot.
And when you plot that data, the initial result is a beautifully straight line leading right up from the origin. The extension increases in equal, predictable steps as the load increases. It is directly proportional. But at a certain point, the graph starts to curve and slope up less steeply. If you're asked to identify this specific point on the exam, this is the limit of proportionality. Beyond this, the spring is permanently damaged, it's inelastically deformed, and it's never going back to its original length. And remember, if an exam asks you to calculate the spring constant, where K equals F over X, you can only do this accurately on the straight, proportional part of the graph. Oh, and stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Okay, let's jump into Section 4, Pressure Under the Surface, where visual imagination becomes your best tool.
Now consider this totally wild, fascinating comparison. Pressure is fundamentally the force acting per unit area at right angles to a surface. That applies whether it's atmospheric pressure pushing liquid up a snorkeler's plastic straw, or the massive weight of a literal elephant underwater using its trunk as a natural snorkel. A large force pressing on a very small area gives a massive pressure. We use that same equation we talked about, P equals F over A. An elephant has an unbelievable weight, sure, but its feet have a massive surface area, which spreads out that force safely across the ground.
Let's really apply this in our Find the Flaw challenge. Imagine you're grading a paper, and a student writes this paragraph. A 600-Newton dancer will cause less damage to a wooden floor than a 5,000-kilogram elephant, simply because the dancer weighs less. Can you spot the flaw that's going to lose them all the marks? The examiner would cross that right out. Why? Because of this staggering number, 6.0 megapascals. A 600-Newton dancer standing on a tiny 1 square centimeter stiletto heel exerts 6 million pascals of pressure. You have to convert that 1 square centimeter into square meters. That's 0.0001 square meters. 600 divided by 0.0001 is 6 million. The dancer will completely punch holes in that floor, whereas the elephant's weight is spread over such a huge area that it results in far less pressure.
Moving into Section 5. When we deal with fluids, Cambridge exams always pull out their absolute highest level command words.
Take a really close look at this dam. Pressure in a fluid does not simply act downwards, it acts equally in all directions, caused by the immense weight of the fluid above it. The deeper you dive, the greater the amount of water physically pressing down on you. This is exactly why this massive concrete dam is designed to be thickest at its base. The equation you need to lock in your memory here is change in pressure equals density times gravitational field strength times change in depth, or delta P equals rho times G times delta H. The depth, h, is the absolute key variable to watch out for.
So, if an examiner uses the command word explain regarding why the dam is built this way, you cannot just casually write because it's deeper. That's a 1-mark answer for a 3-mark question. You must build a logical narrative, you need to set out reasons, make relationships clearly evident, and support everything with actual physics evidence. Let's do a 30-second speed writing challenge right now. Construct a perfect PO paragraph in your head. Ready? Here's the ideal answer. Point. The dam is constructed thicker at the bottom to withstand significantly higher hydrostatic pressure. Evidence. The equation delta P equals rho G delta H shows that pressure is directly proportional to depth. Explanation. Because water has a roughly constant density, as depth increases towards the base, the total weight of the water above increases, creating a massive outward force. Link. Therefore, a thicker, wider base provides the necessary structural integrity to counteract this specific force without collapsing. That right there is how you guarantee maximum marks and leave the examiner speechless.
And the beauty of this framework is that you can apply that exact same peel logic anywhere. For example, to explain why the pressure at the bottom of these two connected water butts is different, you must look at the variables. Both contain water, so density, or rho, is exactly the same. Gravity, g, is the same. The only difference is the depth, h. But A clearly has a higher water level than butt B. Setting out the relationship logically, a greater depth equals a greater weight of fluid above, which definitively equals a greater hydrostatic pressure at the base.
Let's move to Section 6. We are going to take everything we've analyzed today and turn it into a concrete, unbreakable checklist.
So here is your ultimate physics success blueprint. Rule number 1, decode the command word before your pen even touches the paper. Rule number 2, apply the peel framework, especially for those high-value explain and suggest questions. If the word is state, just provide the simple fact and move on. If it says calculate, you show every single data step, formula, and unit, leaving nothing to the imagination. If it says explain, you build that logical narrative we just practiced. And finally, rule number 3 is mastering your time management matrix. Do not spend 5 minutes writing an essay for a 1-mark state question. Mastering this specific blueprint is what pushes your mark potential all the way to 100%. And listen, students who implement these physics strategies see an average improvement of 2 whole grade boundaries, but only if they practice consistently with our weekly videos.
I want to leave you with this final, provocative thought. The next time you sit down with a physics paper, do not just read the problem as a set of random, stressful obstacles. Treat it like a secret code waiting to be cracked. Use the command words as your master key and unlock those top grades you actually deserve. How will you decode the hidden language in your next exam? And here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.